32 trillion tons of matter have disappeared, not exploded, not fragmented into debris field we can track, not sublimated gradually in ways that create visible comet tails and dust clouds, just gone, vanished from an object that we measured carefully, that we tracked with precision exceeding anything we've achieved in the history of observational astronomy, that we thought we understood until the numbers stopped making sense, and we were forced to confront the possibility that everything we believed about what we were observing was wrong. This isn't measurement error. This isn't uncertainty in calculations that might explain discrepancies of a few percent. This is 99%. This is losing essentially all the mass we thought existed. This is watching a mountain disappear while you're staring directly at it, with instruments so sensitive they can detect changes smaller than the width of human hair at distances of millions of kilometers. Hit like and subscribe and know the laws of physics don't allow this. Can't allow objects to shed nearly all their mass in 90 days without consequences we should be able to observe, without explosions, without fragmentation events, without creating debris clouds that would be visible in the careful observations that have been monitoring 3i Atlas continuously since detection. Yet, here we are, confronting data that says the object we measured at 33 trillion kilograms in summer has become 260 billion kilograms by winter. Confronting reality where the 5-kilometer behemoth we were tracking with absolute confidence has somehow transformed into 1-kilometer ghost that moves like it's barely there. And the terrifying part, the detail that keeps pulling me back to this mystery, is that we weren't guessing about the original mass, weren't making rough estimates based on limited observations. We had 230 observatories worldwide pointing instruments at this object for 5 continuous months. Had precision that's almost impossible to comprehend, could measure its position to 0.028 arc seconds. To put that in terms that make sense, if you could achieve that level of precision with your eyes, you could spot a coin lying on sidewalk from 100 kilometers away. Could resolve details that are invisible to any natural human perception. Could track this object with accuracy that eliminates any possibility of major error in determining where it was and how it was moving. Before we go further, before we dive into how 32 trillion tons vanish without trace and what that impossibility might mean, you need to subscribe to this channel right now. Because what we're documenting isn't just interesting astronomy story, isn't just unusual object with properties we don't fully understand. This is potential breakdown of our physical understanding. This is observation that violates what we thought were inviolable constraints. This is evidence that either our physics is incomplete or that we're observing something that operates according to principles we haven't encountered before. And if you want to follow this investigation as it develops, as we continue tracking 3i Atlas, and as we attempt to resolve contradictions that currently make no sense, you need to be here. Hit subscribe, enable notifications. This matters too much to miss. The summer observations established baseline, created foundation for everything we thought we knew about this object. Because from May through September, as 3i Atlas approached the inner solar system, as it moved through regions where solar radiation and solar wind create forces that affect how objects move, we watched it carefully, monitored it continuously, tracked every detail of its trajectory to see whether it was following purely gravitational path or whether non-gravitational forces were affecting its motion, and the answer was unambiguous. The object moved exactly where gravity predicted it should move, not approximately, not close enough that we could claim the deviations were within measurement uncertainty. Exactly. To precision that exceeded our ability to detect deviations that were 300 times smaller than the accelerations we're now measuring. If there had been any push from outgassing, any force from solar radiation pressure overcoming the object's inertia, any deviation from purely gravitational trajectory no matter how subtle, we would have seen it. Our instruments were sensitive enough. Our observation campaign was comprehensive enough. The detection limits were established rigorously through statistical analysis of the measurements, but we detected nothing, zero non-gravitational acceleration. Perfect agreement between observed positions and calculated gravitational trajectory. And that silence, that absence of any observable push from solar radiation or from gas being ejected from the surface, told us something definitive about the object's mass. Because in physics, silence tells story, particularly when you're expecting noise and you get perfect quiet instead. The logic is straightforward. Solar radiation carries momentum. Photons striking an object's surface transfer their momentum to that object, create force that's small but measurable for objects that aren't too massive. For lightweight objects, for things with low mass relative to their surface area, radiation pressure creates significant acceleration. For massive objects, for things that are heavy enough that their inertia overwhelms the gentle push of sunlight, radiation pressure creates negligible effect. So by measuring whether an object accelerates under radiation pressure or whether it maintains purely gravitational trajectory, you can constrain its mass. And 3I Atlas wasn't accelerating, wasn't showing any response to solar radiation despite being in region where that radiation is intense enough to create measurable forces on objects with typical cometary properties, which meant it had to be massive, had to be heavy enough that the momentum transfer from sunlight was insufficient to alter its trajectory detectably, had to have enough inertia that it could ignore the constant bombardment of photons that should have been pushing it gently but measurably off the purely gravitational path. Scientists ran the calculations, crunched the numbers based on the absence of detectable acceleration and on the precision with which we'd measured that absence, and the results were clear. For 3I Atlas to remain unresponsive to solar radiation pressure at the levels our instruments could detect, it needed to be roughly 5 kilometers in diameter, needed to be mountain-sized chunk of material, needed to have mass approaching 33 trillion kilograms, 33 billion tons, more massive than many asteroids in our own solar system, a genuine giant drifting through the void. That calculation wasn't speculation, wasn't rough estimate that might be off by factors of 2 or 3. It was rigorous derivation from well-understood physics applied to high-quality observational data. The absence of acceleration constrained the mass-to-area ratio. The assumed density typical of cometary material converted that ratio into absolute mass estimate. And while there was uncertainty in the density assumption, while we couldn't be completely certain whether the object was pure ice or a rocky mixture or something else, that uncertainty affected the mass estimate by maybe factor of 2. Maybe you could argue it was 20 trillion kilograms instead of 33 trillion, or maybe 50 trillion. But you couldn't make it orders of magnitude different without violating the observational constraints. So we were confident, were certain we'd measured giant correctly, had built our understanding on solid foundation of comprehensive observations and rigorous analysis, knew that 3I Atlas was massive object, knew it with confidence that comes from having data that's consistent and unambiguous, and that confidence, that certainty grounded in hundreds of observations from dozens of facilities, all telling the same story, is what makes the subsequent discovery so devastating. Because we weren't wrong about the measurements, weren't misinterpreting the data, but we were completely wrong about what we were actually observing. The 5 months of silence were punctuated by regular measurements confirming that nothing was changing, that the trajectory remained purely gravitational, that the object continued behaving exactly like massive inert body should behave when passing through the solar system. No surprises, no anomalies, no deviations that would require revision of our understanding. Just confirmation after confirmation that our model was correct, that we were tracking 5-kilometer mountain, that the mass estimate of 33 trillion kilograms was solid. But silence can be misleading, can create false confidence when you interpret it through framework that might not apply, because we were assuming that the silence meant the object was simply massive and inert, that it was typical interstellar wanderer, that it would continue behaving predictably according to natural processes we've observed countless times in solar system comets and asteroids. We were fitting observations into comfortable framework where everything made sense, and where our physics worked perfectly, and maybe that assumption was our first mistake. Maybe interpreting silence as simple inertness rather than as something more complex was where we went wrong, because as 3I Atlas continued inward, as it approached perihelion and began experiencing more intense solar heating, the giant we thought we knew started doing something that shattered every model we'd built, started showing behavior that contradicted everything the summer observations had established, started demonstrating that whatever we'd been tracking for 5 months wasn't what we thought it was. The transition wasn't gradual, wasn't slow evolution where we could watch the object change incrementally and adjust our understanding progressively. It was sudden recognition when new observations became available that the reality didn't match expectations, that something fundamental had changed or that we'd been misunderstanding fundamentally from the beginning, and confronting that realization, accepting that our confident conclusions from summer were completely wrong, required acknowledging that 32 trillion tons of matter had vanished or had never existed in the first place. December brought James Webb Space Telescope measurements that should have been routine characterization, should have provided detailed spectroscopy confirming composition, should have measured outgassing rates and velocities to understand how the object was responding to solar heating as it passed perihelion, should have been collecting data that would refine and extend our summer observations rather than completely contradicting them. But the measurements Webb returned weren't refinements, were contradictions, were observations that couldn't be reconciled with the massive object we'd been tracking, because Webb detected acceleration, measured that 3I Atlas was being pushed, was deviating from purely gravitational trajectory in ways that our summer observations had established weren't happening, but that were definitely happening now. The object was gaining 13 kilometers per day of additional velocity, small acceleration, tiny compared to gravitational forces, but unambiguous, measurable, real, and that acceleration, combined with the spectroscopic measurements of how much gas was being ejected and at what velocity, forced complete recalculation of the mass. Because the physics is deterministic, is unambiguous. When you measure how much force is being applied through gas ejection, when you measure the resulting acceleration, the mass is just ratio between them. Newton's second law. Force equals mass times acceleration. Rearrange, and you get mass equals force divided by acceleration. Plug in the measured values and you get answer that doesn't care about what you thought the mass should be. Just tells you what it must be to produce observed acceleration from measured force. And the answer was devastating, was incompatible with everything we'd established during summer. Because to get 13 kilometers per day acceleration from the gas being ejected at rates and velocities Webb measured, the mass couldn't be 33 trillion kilograms, couldn't be anywhere close to that, had to be 260 billion kilograms, had to be 120 times less than summer observations indicated. Had to be small light object rather than massive mountain. The diameter calculation followed automatically, because if mass is 120 times smaller, and if density is assumed to be similar to what we'd assumed before, then volume must be 120 times smaller, and volume scales as the cube of linear dimension. So reducing volume by factor of 120 means reducing diameter by cube root of 120, which is approximately 5. The 5-kilometer behemoth becomes 1-kilometer fragment, the mountain becomes boulder, the giant becomes ghost, and this isn't uncertainty, isn't measurement error that might explain factors of 2 or 3 difference, is order of magnitude discrepancy, is factor of 120 that can't be explained away through improved measurements or refined analysis. Either the summer observations were completely wrong about the mass, which seems impossible given how comprehensive and precise they were, or the winter observations are completely wrong about the acceleration and outgassing, which seems impossible given Webb's capabilities, or something changed between summer and winter that caused the object to lose 99% of its mass without creating observable consequences. Or we're not observing what we think we're observing, are misunderstanding fundamentally what 3I Atlas actually is, are trying to force reality into framework that doesn't apply, are using tools designed for measuring rocks and ice to characterize something that might be neither. The vanishing mass creates paradox that physics doesn't easily resolve, because 32 trillion tons is an enormous amount of matter. Is mountain range worth of material? Is mass that doesn't just disappear quietly? If that much material sublimated, if it turned from ice to gas and dispersed, we'd see comet tail that would be visible from Earth without telescopes, would see dust clouds and gas clouds creating structures that dominate the object's appearance, would have obvious visual signature of massive outgassing event. But we see modest activity, see outgassing that's measured in hundreds of kilograms per second, rather than in megatons per second, that would be required to lose 32 trillion tons over a 90-day period. See comet tail and coma that are typical for small active comet rather than seeing unprecedented display that shedding mountains worth of material should create. See nothing that would indicate the object is undergoing catastrophic mass loss on scale required to explain the discrepancy. And if the mass loss wasn't through sublimation, if it was through fragmentation, where solid material broke apart and dispersed, we'd see debris, would detect fragments, would observe cloud of smaller pieces surrounding the main nucleus, Would have radar returns and visual observations showing that the object has broken into multiple components. But we see none of that. See single object, no debris field, no companion fragments, no evidence whatsoever of catastrophic breakup that would be required to shed 32 trillion tons. So if the mass didn't sublimate and didn't fragment, if it didn't leave through any process that physics allows and that observations would detect, then where did it go? How do you lose 99% of your mass without trace? How do you make 32 trillion tons disappear without violating conservation of mass that's fundamental principle of physics? How do you reconcile observations that unambiguously indicate the object was massive in summer with observations that unambiguously indicate it's lightweight in winter? The comfortable answer is that we made mistake, that the summer mass estimate was wrong despite being based on comprehensive observations and rigorous analysis, that somehow we misinterpreted the absence of acceleration, that there are processes or conditions we didn't account for that make the mass estimate unreliable. This is what conventional scientific thinking demands. That we find error in our analysis rather than accepting that physics is violated or that we're observing something anomalous. But finding that error is proving difficult, because the summer observations really were comprehensive, really did achieve the precision claimed, really did establish detection limits that make it essentially impossible for significant acceleration to have been occurring without being detected. The observation campaign was specifically designed to catch subtle effects, was optimized for detecting exactly the kind of deviations that we now know exist, and it detected nothing, which means either our instruments were systematically wrong in ways we don't understand, which seems unlikely given that multiple independent facilities all reported consistent results, or the acceleration genuinely wasn't occurring during summer, which brings us back to the impossible scenario, where the object was massive and inert during summer observations, where it became lightweight and active during winter observations, where something changed fundamentally between the two observation campaigns, where 32 trillion tons either vanished or never existed, where our physics either breaks down or our assumptions about what we're observing are completely wrong. And that impossibility is what makes this so disturbing, because physics doesn't usually present us with contradictions this stark, doesn't usually put us in situations where high-quality observations using well-understood techniques produce results that are mutually incompatible, doesn't usually force us to choose between accepting that matter can disappear without trace, or accepting that we don't understand what we're looking at all. Usually there are explanations that resolve apparent contradictions. Usually more careful analysis or additional observations clarify which interpretation is correct. But with 3i Atlas, the contradiction remains, persists despite attempts to find resolution, stands as genuine paradox where the data forces conclusions that are incompatible with each other and where neither can be easily dismissed as erroneous. We measured a giant. We measured a ghost. Both measurements were rigorous. Both appear valid. Yet they can't both be describing the same object unless that object changed in ways that violate our understanding of how matter behaves. The fluffy comet hypothesis is the most conservative attempt to resolve the paradox naturally. The idea is that 3i Atlas isn't solid ice or rock, is instead extremely porous material, structure that's more void than substance, like aerogel or styrofoam but at scales relevant to kilometer-sized objects, where the volume is mostly empty space with ice forming delicate framework that gives the object its size while keeping the mass low. This would mean the summer mass estimate was wrong because we assumed typical cometary density. Assumed the 5-kilometer diameter corresponded to solid or moderately porous material, but if actual density is orders of magnitude lower than typical values, if the object is 99% void, then the mass could be much lower than calculated while the size remains large enough to explain why we observed the object as we did. The hypothesis has appeal, explains the mass discrepancy without requiring violation of physics or acceptance of artificial origin, keeps everything within natural framework where exotic but possible processes account for observations, allows us to maintain comfortable assumption that we're studying natural interstellar comet rather than confronting alternative interpretations that are more unsettling. But the hypothesis has problems, has challenges that make it less satisfying solution than it initially appears, because fluffy comet doesn't naturally explain why the acceleration was absent during summer. If the object was always lightweight, if the mass was always 260 billion kilograms rather than 33 trillion, then solar radiation pressure should have been accelerating it during summer observations. should have created detectable non-gravitational trajectory deviations that our instruments were sensitive enough to detect. Yet we detected nothing, which means either the fluffy comet was somehow shielded from radiation pressure during summer, which requires mechanism we don't understand, or the outgassing was perfectly balanced such that forces cancelled and produced zero net acceleration despite object being lightweight, which requires extraordinary coincidence, or the mass actually was higher during summer and genuinely decreased through processes that removed material without creating observable signatures, which returns us to the impossible vanishing mass scenario. So the fluffy comet hypothesis doesn't actually resolve the paradox cleanly, just shifts it, transforms the question from where did the mass go to why didn't lightweight object accelerate when it should have. Both questions are difficult. Both require explanations that invoke processes or conditions we don't fully understand. Neither provides satisfying resolution that makes everything make sense within comfortable natural framework. And when your explanation creates as many new problems as it solves, when it requires invoking circumstances that are themselves difficult to justify, you have to question whether you're actually on the right track, or whether you're just defending preferred interpretation despite evidence suggesting you should consider alternatives. The hidden outgassing hypothesis attempts to explain the summer silence differently, proposes that acceleration was occurring, but that we couldn't detect it because the forces were arranged such that they cancelled from our perspective, like having jets firing in multiple directions simultaneously, such that the net thrust is small or zero, even though individual jets are creating significant forces. This would allow the object to be lightweight while explaining why we didn't detect acceleration during summer observations. But this hypothesis also has challenges, requires that the outgassing configuration during summer was dramatically different from winter configuration, requires that jets were positioned and oriented such that they produced near-perfect cancellation despite the object rotating and despite different surface regions being illuminated at different times, requires stability in this cancellation over 5 months, during which rotation should have changed which regions were active and should have broken any coincidental force balance, and requires explaining why the configuration changed between summer and winter such that winter shows clear net acceleration while summer showed none. Each of these requirements is possible individually. Jets can fire in multiple directions. Forces can partially cancel. Configurations can change as objects evolve, but requiring all of them simultaneously, requiring that everything aligned perfectly during summer to hide the acceleration and then change dramatically by winter to reveal it, stacks coincidences in ways that make the explanation feel contrived, feel like we're fitting the theory to match observations rather than observations confirming predictions from theory we understood before measuring. And there's the deeper problem that both natural explanations, fluffy comet and hidden outgassing, require that the summer observations were somehow misleading. That despite achieving unprecedented precision, despite having 230 observatories tracking the object continuously, despite detection limits that were 300 times more sensitive than the accelerations we're now measuring, we somehow missed what was actually happening. That our instruments or our analysis or our interpretation was systematically wrong in ways that made lightweight active object appear as massive inert one. That's technically possible. Science progresses by discovering that previous measurements were wrong or incomplete, by finding that what seemed certain based on available data was actually misleading, because we didn't understand all the factors that were relevant. History is full of examples where confident conclusions had to be revised when better observations became available. So claiming that summer observations were misleading despite their quality isn't inherently unreasonable. But it is uncomfortable, is exactly the kind of revision that we resist because accepting it means accepting that our most careful work might be fundamentally wrong, that even when we do everything right, even when we achieve precision that seems more than adequate, we might be missing crucial aspects of what we're observing, that our understanding might be incomplete in ways we don't recognize until contradictions force us to reconsider everything. And that discomfort, that resistance to accepting that we might be completely wrong despite high-quality data, is what keeps many researchers defending natural explanations, even when those explanations require increasingly exotic assumptions. The artificial hypothesis takes a completely different approach, stops trying to explain how natural processes could reconcile the contradictory mass measurements, and instead proposes that the contradiction disappears if we accept that 3i Atlas isn't a natural object. if we recognize that we're observing technology rather than geology. If we understand that the mass discrepancy reflects our misunderstanding of what we're measuring rather than representing physical impossibility. The logic is straightforward. If 3i Atlas is hollow shell rather than solid object, if it's manufactured structure with large volume but low mass like balloon or sail, then the summer observations would naturally show no acceleration because the object was configured to maximize mass during that phase of its trajectory, was operating in mode where it maintained heavy appearance, was deliberately staying quiet to avoid detection or to achieve some operational objective that required maintaining stable gravitational trajectory, and then as it approached perihelion, as it moved into region where mission parameters required different configuration, it transitioned to lightweight mode. Reduced apparent mass, allowed solar radiation pressure and outgassing thrust to accelerate it, created the behavior we observe in winter that contradicts what we observed in summer, not because physics broke down, but because the object is a controlled system that operates in different modes depending on mission requirements. This explanation unifies the observations, makes both summer and winter data-valid representations of what was actually happening rather than requiring that one set be wrong. Explains why acceleration appeared suddenly rather than gradually, as would be expected if natural processes were responsible. Explains why the mass appears to have changed by factor of 120 when matter doesn't actually vanish. Because in artificial scenario, matter didn't vanish. The mass was never 33 trillion kilograms. We just calculated wrong mass because we assumed we were observing solid object when we were actually observing hollow structure that was presenting large cross-section while maintaining low mass. The light sail analogy makes this concrete. Imagine structure like solar sail that spacecraft use for propulsion, thin reflective membrane stretched across large area. From distance, measuring how much sunlight it reflects, you might estimate its size correctly. But estimating its mass, assuming it's solid object, would give completely wrong answer. Because sail is almost all area and almost no mass, is specifically designed to maximize surface area relative to mass to achieve high acceleration under radiation pressure. If 3i Atlas is similar structure, if it's artificial sail or shell designed to interact with solar radiation and solar wind, then during summer it might have been configured to minimize that interaction, might have been oriented edge onto radiation, might have had surface properties that reduced pressure coupling, might have been operating thrusters or other systems that counteracted radiation pressure to maintain zero net acceleration, all of which would make it appear massive because we'd interpret the lack of acceleration as indicating high inertia. But approaching perihelion, mission parameters change. The object needs to adjust its trajectory, needs to use solar radiation and solar wind for propulsion, so configuration changes. Surface is oriented to maximize pressure coupling, counteracting systems are shut down. The structure operates in mode where radiation pressure creates significant acceleration, and we observe lightweight object being pushed around by forces that weren't affecting it previously, not because the mass changed, but because the operational mode changed. This is speculative. It's hypothesis that requires accepting extraordinary conclusion that we're observing artificial interstellar probe rather than natural comet. But it's speculation that fits all the observations, that explains summer silence and winter activity as different operational modes rather than as contradictory measurements of the same physical property. That makes the mass discrepancy comprehensible as our error in interpretation rather than as impossible violation of conservation of mass. That provides unified framework where everything we've measured is valid data about object that's just not what we assumed it was. And the terrifying aspect, the detail that makes this hypothesis so disturbing to contemplate, is that it suggests we were fooled, that the object deliberately appeared as massive natural body during initial observations, that it maintained that appearance for 5 months while we tracked it confidently, that it only revealed its true nature, only showed that it was lightweight and active and potentially artificial, after it had passed the point in its trajectory where we could easily intercept or interfere. That if it is technology, it successfully executed camouflage strategy that made it look natural until it was ready to demonstrate otherwise. That level of sophistication, that kind of deliberate deception if that's what it was, implies intelligence operating on timescales and with planning capability that we can barely comprehend. Implies that the object knew it was being observed, knew what kinds of measurements we were making, knew how we would interpret those measurements if it maintained certain behavior, an executed mission profile that took all of that into account, that used our own observational capabilities and our interpretive frameworks against us to maintain cover until cover was no longer necessary. This isn't wild speculation, isn't inventing capabilities without reason. Is logical inference from what would be required to produce the observations we've actually made. If the object is artificial, and if it wanted to avoid detection or interference during approach phase, maintaining appearance of massive inert body is exactly the strategy it should employ. Because massive objects are boring, are predictable, are things we catalogue and track but don't worry about, don't trigger the kind of attention and response that obviously anomalous object might provoke, so you drift through the outer solar system looking like rock, moving on purely gravitational trajectory that matches predictions perfectly, giving observers no reason to suspect anything unusual, letting them measure you carefully and conclude confidently that you're just another interstellar visitor, just unusual for being interstellar, but not unusual in behaviour, not threatening, not worth more than scientific curiosity. And then once you're deep in the inner solar system buried, once you've completed whatever observations or objectives required being in specific locations at specific times, once interference would be difficult even if it were attempted, you drop the pretense. You configure for departure. You let acceleration become visible. You demonstrate that you're lightweight and active and not at all what the confident measurements concluded. You reveal that the observers were wrong about fundamentally important aspects of what they were observing. That revelation serves multiple purposes if it's deliberate, demonstrates capability, shows that you can operate covertly when needed, shows that the observer's confidence in their measurements can be manipulated, shows that what they think they know might not be reliable, all of which affects how they respond to future encounters. All of which influences their assessment of whether similar objects they detect later might also be artificial, all of which shapes the relationship between observed and observer in ways that might serve strategic objectives we can't fully understand. But maybe that's reading too much intention into observations that might have simpler explanations. Maybe the apparent deception is coincidence rather than strategy. Maybe the object was always lightweight and the summer measurements just happened to miss the acceleration through combination of unfortunate circumstances that aren't understood yet, but that don't require invoking artificial intelligence deliberately fooling observers. Maybe we're projecting human concepts of camouflage and strategy onto natural object that's just behaving according to processes we don't understand. The challenge is determining which interpretation is more likely, whether natural explanation requiring exotic circumstances and measurement errors is more probable than artificial explanation requiring acceptance that we're observing technology. Traditional scientific reasoning strongly favours natural, requires exhausting all possible natural explanations before considering artificial, demands that extraordinary claims like artificial interstellar probe require extraordinary evidence before being accepted. But how much evidence is required? What constitutes extraordinary enough proof? We have mass measurements that contradict each other by factor of 120. We have trajectory behaviour that changed dramatically between observation campaigns. We have object that appeared to lose 32 trillion tons of matter without creating observable signatures of that loss. We have pattern of anomalies, where each new measurement adds features that natural framework struggles to explain while artificial framework accommodates straightforwardly. At what point does continued insistence on natural explanation stop being appropriate scientific caution and start being ideological commitment? At what point does the accumulation of anomalies that individually might be explicable but collectively create overwhelming pattern become sufficient to justify reconsidering the framework entirely? At what point do we accept that maybe, just maybe, we're not observing what we think we're observing and that the artificial hypothesis deserves serious consideration rather than dismissal as fringe speculation? These are questions the scientific community is struggling with regarding 3i Atlas. Questions that don't have clear answers because the standards for accepting artificial origin haven't been established. Because we've never been in a situation where we had observations of potential extraterrestrial technology that were detailed enough to evaluate rigorously. Because all previous cases like Oumuamua remained ambiguous enough that both natural and artificial interpretations could coexist without definitive resolution. But the mass paradox is pushing toward resolution, is creating a situation where ambiguity becomes harder to maintain, where either we find natural explanation that actually works, that actually accounts for all observations without requiring stacked coincidences and exotic processes, or we accept that natural framework is inadequate and that we need to seriously consider artificial origin not as speculation, but as most probable explanation for what we're actually observing. The timeline of observations creates narrative that's hard to escape. May through September, massive silent object following gravitational trajectory perfectly. No activity, no outgassing, no acceleration. Just mountain drifting through void exactly as gravity predicts. We measure it confidently, calculate its mass at 33 trillion kilograms based on its resistance to solar radiation pressure. Build understanding on foundation of comprehensive high-precision observations that all tell consistent story. October through November, approach to perihelion. Solar heating intensifies. We expect activity to begin. Expect to see outgassing as volatiles sublimate. Expect acceleration to appear as gas jets create thrust. We watch carefully for these transitions, for the moment when the quiet mountain becomes active comet, for the changes that should occur as solar energy input increases. December. James Webb measurements reveal acceleration, reveal that object is being pushed by outgassing at rates that indicate mass must be 260 billion kilograms rather than 33 trillion. Reveal that everything we thought we knew about this object's mass is wrong by factor of 120. Reveal that 32 trillion tons of matter have vanished or never existed. Reveal paradox that physics doesn't explain and that natural framework struggles to accommodate. January. We're here, trying to make sense of observations that don't fit together, trying to determine whether massive error occurred in summer measurements despite their quality, trying to understand how object could transition from heavy to light without observable consequences, trying to decide whether natural explanations involving fluffy structure or hidden outgassing are adequate, or whether we need to seriously consider that we're observing artificial probe that deliberately appeared massive during approach and lightweight during departure. And the object is leaving, is moving outward on trajectory that will eventually take it back to interstellar space. Is departing before we've resolved the questions its behavior raises. Is escaping while we're still debating what it actually is. We have limited time remaining to make additional observations. Limited window to collect data that might distinguish between competing explanations. Limited opportunity to answer questions before the object becomes too distant to study effectively. That urgency compounds the pressure to reach conclusions, creates environment where we're forced to make decisions about how to interpret ambiguous evidence before we have all the information we'd prefer to have, where we choose between accepting that measurements might be wrong despite appearing valid or accepting that object might be artificial despite how extraordinary that conclusion is, where we commit to frameworks that will shape how we understand not just this object, but future interstellar visitors and our cosmic context more generally. The mass loss rate that Webb measured provides another piece of the puzzle that doesn't quite fit. 150 kilograms per second sounds substantial, sounds like significant outgassing that should create visible effects. And over the 90 days between summer observations and winter measurements, 150 kilograms per second accumulates to substantial total. Calculate it. 150 times 60 seconds per minute times 60 minutes per hour times 24 hours per day times 90 days comes to roughly 1 billion kilograms, 1 million tons. That's substantial mass loss, is amount that should create observable effects if it's being ejected into space. Should create comet tail, should create coma, should produce visual signatures that confirm major outgassing is occurring. And we do see those signatures. Do observe tail and coma consistent with 150 kilograms per second mass loss. So that measurement seems validated by observations. But 1 billion kilograms is tiny compared to 32 trillion kilograms, is 3/10,000ths of 1%. Is rounding error relative to the discrepancy we're trying to explain? If the object actually lost 32 trillion tons between summer and winter, the mass loss rate would need to be not 150 kilograms per second, but 30,000 times higher. Would need to be 5 million kilograms per second, would need to be creating outgassing display that would be visible from Earth without telescopes. Would need to be producing effects that would dominate the sky. And we see nothing like that. See modest comet activity consistent with measured 150 kilograms per second loss. See nothing that would indicate the catastrophic mass loss required to actually lose 32 trillion tons. which means the mass didn't actually vanish through sublimation. Couldn't have vanished through sublimation, because the observed outgassing is orders of magnitude too small. So if it didn't sublimate and it didn't fragment and it didn't explode, if none of the mechanisms that could actually remove that much mass from object operated, then where did it go? How do you make 32 trillion tons disappear when all the processes that could remove it are observably not occurring at the rates required? How do you reconcile observations that say the mass must have changed with observations that say the mass couldn't have changed through any known mechanism? That's the heart of the paradox. That's the contradiction that makes this so difficult to resolve within natural framework. Because physics gives you limited menu of ways that objects can lose mass: sublimation, fragmentation, collision, explosion. Each has observable signatures. Each creates effects we can detect. And when you look for those effects, when you search for evidence that any of these mechanisms operated at scales required to lose 32 trillion tons, you find nothing. Find only the modest activity consistent with losing billions of kilograms through normal cometary outgassing, rather than trillions of kilograms through catastrophic process. Which forces conclusion that the mass didn't actually change, that 32 trillion tons didn't vanish because they were never there, that the summer mass estimate was wrong, not because measurements were bad, but because assumptions about what was being measured were wrong. That we calculated 33 trillion kilograms because we assumed solid object when we should have been assuming hollow structure or sail, or some other configuration where volume doesn't correlate with mass in ways we expected. And that conclusion, that recognition that our fundamental assumptions about what we were observing were wrong, is what makes the artificial hypothesis so compelling. Because artificial objects can be hollow, can be designed to have large volume and small mass, can be configured to present different apparent properties depending on operational mode, can do exactly what 3i Atlas appears to have done, look massive when operating in one mode, and lightweight when operating in another without actually changing its mass at all. The velocity measurements provide additional layer of evidence that complicates the natural interpretation while supporting the artificial hypothesis. Because Webb didn't just measure how much gas was being ejected, also measured how fast it was moving, found that material was leaving the surface at 1600 kilometers per hour, 445 meters per second. That's fast. Is significantly faster than typical cometary outgassing where thermal sublimation produces velocities around few hundred meters per second for common volatiles like water or carbon dioxide. For carbon dioxide specifically, thermal velocity at temperatures you'd expect on comet's surface at the distance 3i Atlas was from the Sun calculates to around 250 meters per second. That's maximum speed that CO2 molecules achieve when sublimating from ice that's been heated by sunlight. Its thermodynamic limit determined by how much kinetic energy molecules have at given temperature. You can't exceed it without adding energy beyond what solar heating provides, without accelerating the molecules through some additional mechanism, but Webb measured 445 meters per second, nearly twice thermal velocity. Nearly twice what natural sublimation can produce. This isn't small discrepancy, isn't measurement uncertainty that might explain 10 or 20% difference, is factor of 2 excess velocity that requires explaining. That indicates something beyond thermal sublimation is accelerating the gas. That suggests processes are operating that we don't see in normal comets and that don't fit natural framework comfortably. Natural explanations for excess velocity exist, could invoke superheated vents where localized heating exceeds average surface temperature and produces faster molecules, could invoke gas accelerating through narrow channels where pressure differences create jet effects, could invoke chemistry beyond simple sublimation where chemical reactions release energy that gets converted to kinetic energy in ejected material. Each mechanism is possible, each has been observed in some contexts, each could potentially explain velocities somewhat higher than simple thermal calculations predict, but factor of 2 is challenging, requires that these enhancement mechanisms are operating very efficiently, that whatever is adding energy to the gas is doing so systematically across the entire outflow rather than just in isolated vents or regions, that the process is stable enough to produce consistent velocity measurements rather than showing large variations that would indicate chaotic enhancement from multiple competing mechanisms. And even if you accept that natural processes can produce the observed velocities, even if you construct scenario with superheated vents or accelerating jets or energetic chemistry, you still need to explain why this is happening on 3i Atlas when it's not typical of other comets. Why this particular object shows enhancement that others don't. Whether there's something special about its composition or structure or formation history that makes it different. Whether the processes that create excess velocity are rare enough that seeing them requires observing interstellar visitor rather than being common enough that we'd see them frequently in solar system comets. Artificial propulsion naturally produces high exhaust velocities, is designed to maximize velocity because that maximizes efficiency for given propellant mass. Chemical rockets achieve velocities of few kilometers per second. Ion drives achieve tens of kilometers per second. Even relatively simple propulsion systems exceed thermal sublimation velocities substantially. So if the outflow from 3i Atlas is exhaust from propulsion system, rather than natural sublimation, velocities higher than thermal aren't surprising, are exactly what you'd expect, and 445 meters per second sits in interesting region, is faster than thermal, but slower than most efficient propulsion systems we've developed. Could represent deliberately throttled propulsion, could represent system that's operating at partial power, because full power isn't needed for current maneuver, could represent technology that's more efficient than chemical rockets but less efficient than ion drives, could represent exhaust from system we don't understand that operates according to principles we haven't discovered, all speculation. All building scenarios on top of limited measurements, but the speculation is constrained by what we actually observe, by the fact that velocity is higher than thermal, by the fact that it produces acceleration consistent with lightweight object, by the fact that the behavior appeared suddenly rather than gradually, by all the details that individually might be explicable naturally, but that collectively create pattern, suggesting engineering rather than geology. The trajectory evolution after perihelion provides additional data point, because we're now tracking the object as it moves outward, as it recedes from the Sun and heads back toward interstellar space. And we can measure whether the acceleration continues, whether it increases or decreases, whether it shows patterns that indicate natural outgassing responding to changing solar heating, or whether it shows patterns that suggest active control, adjusting thrust for navigational purposes. Preliminary indications are that acceleration is continuing, is persisting as the object moves outward despite decreasing solar heating, that should reduce outgassing if natural processes dominate. Natural comet should show activity declining as solar distance increases, should show acceleration decreasing as sublimation rates drop with reduced heating, should follow predictable pattern where everything scales with solar illumination intensity according to well-understood physics. But if acceleration remains constant or changes in ways that don't correlate with solar distance, if it shows modulation that suggests active control rather than passive response to environment, that's additional evidence favoring artificial origin. That's behavior that natural framework struggles to explain while artificial framework accommodates naturally. That's exactly what you'd see if the object is maneuvering, is using propulsion to adjust trajectory according to mission plan rather than just responding to solar heating. The data isn't complete yet. Need more observations over longer period to establish whether patterns exist or whether the acceleration evolution is consistent with natural processes. But the fact that we're seeing continued acceleration at all, that the object remains active as it moves outward, is notable, is worth monitoring carefully, is exactly the kind of observation that could distinguish between competing hypotheses if patterns emerge that clearly favor one interpretation over the other. The rotation state provides another observable that might reveal whether we're dealing with natural or artificial object. Natural tumbling asteroid shows chaotic rotation, shows multiple axes with different periods, shows evolution as tidal forces, and outgassing create torques that change the spin state. Shows exactly the kind of complexity that you get from a regular object responding to external forces without any mechanism to maintain stable orientation. Controlled spacecraft shows stable rotation, shows single primary axis with consistent period, shows resistance to perturbations because control systems counteract torques and maintain desired orientation. Shows exactly the kind of organization that you get from engineered object with attitude control systems operating to keep instruments pointed correctly, or to maintain orientation that optimizes solar power collection, or thermal management or any of the other operational considerations that designed system needs to address. Current measurements show that 3i Atlas rotates, has period that's been characterized, but detailed analysis of rotation state determining whether it's simple rotation around single axis or complex tumbling determining whether the period is stable or evolving, determining whether there's wobble or precession, or other features that indicate uncontrolled motion versus stable orientation. All of that requires careful analysis of how brightness varies over time and how that variation correlates with viewing geometry. That analysis is ongoing, is being conducted by researchers who understand how to extract rotation parameters from photometric data, but results aren't definitive yet, haven't established clearly whether rotation is consistent with natural tumbling or with controlled orientation, haven't provided clear discrimination between hypotheses based purely on rotation behavior. So rotation remains another observable that might eventually contribute to resolving the question, but that currently doesn't strongly favor either interpretation. The color measurements provide information about surface composition and properties. Natural comets show colors that reflect the mix of ice and dust and organic compounds that make up their surfaces, show variations across the coma as different materials sublimate at different rates and create regions with different compositions, show changes over time as surface evolution exposes fresh material or as mantling by less volatile compounds changes what's visible. Artificial surfaces might show different colors, might be designed to have specific reflective properties that optimize interaction with solar radiation, might show uniformity that indicates manufacturing rather than natural accretion, might show colors that don't match any natural material we've studied. All speculative. All depending on what materials advanced civilization might choose for constructing interstellar probe and how those materials would appear in telescopic observations. Current color measurements show that 3i Atlas appears relatively neutral, doesn't show strong color indicating it's very red or very blue, falls within range of colors that solar system comets exhibit, doesn't immediately stand out as anomalous based on color alone. So this observable doesn't currently provide strong evidence either way, doesn't rule out natural or artificial, just confirms that whatever the object is, its surface reflects sunlight in ways that aren't wildly different from what we see on other small bodies. But neutral color could itself be significant if we're looking at artificial object, because if you're designing probe to appear natural, if camouflage is objective, then matching colors of typical comets would be deliberate choice, would be detail that helps you blend in. That prevents observers from immediately recognizing something unusual based on visual appearance alone. So absence of color anomaly doesn't necessarily support natural interpretation, could equally support artificial interpretation, where matching natural appearance was design requirement. Every observable becomes ambiguous when you're trying to distinguish between natural object that happens to have unusual properties and artificial object that's designed to appear natural until revealing itself becomes necessary or advantageous. Because good camouflage mimics the thing it's trying to resemble as closely as possible, makes detection difficult not by being invisible, but by being indistinguishable from natural background. And if 3i Atlas is camouflaged probe, then expecting it to have obvious artificial signatures visible in standard observations is naive, is looking for exactly the features that good camouflage would hide. So how do you detect camouflage? How do you recognize the object appearing natural is actually artificial when all the individual measurements return values consistent with natural interpretation? You look for patterns, look for combinations of features that individually are explicable but collectively are improbable. Look for behaviors that are possible naturally but that are expected artificially. Look for evolution that shows organization rather than chaos. Look for exactly the kinds of things that 3i Atlas is demonstrating through the mass paradox and the velocity excess and the trajectory evolution and all the accumulated anomalies. The scientific method struggles with camouflage scenarios, struggles with cases where null hypothesis, the assumption of natural origin, is specifically what the phenomenon is designed to mimic, because the methodology is built on falsification, on testing predictions and rejecting hypotheses when predictions fail. But if artificial object is deliberately designed to pass tests that natural objects would pass, then those tests don't falsify artificial hypothesis, don't provide discrimination, just confirm that camouflage is working. Breaking through camouflage requires different approach, requires looking for inconsistencies, for places where the disguise isn't perfect, for features that are challenging to mimic or that reveal themselves through behavior rather than through static properties. The mass paradox is exactly this kind of inconsistency, is place where maintaining appearance of massive natural object conflicted with demonstrating lightweight active behavior necessary for mission objectives, is crack in the disguise where the reality underneath becomes visible, And once you see one crack, once you recognize that object isn't quite what it appears to be, you start looking more carefully at everything else. Start questioning assumptions. Start asking whether other features that seemed natural might actually be artificial aspects of camouflage that you accepted uncritically. Start building different picture where apparent anomalies aren't puzzling exceptions to natural behavior, but are instead signatures of artificial system that isn't quite perfect in mimicking natural appearance. This is the psychological transition that makes accepting artificial origin so difficult, because it requires reversing gestalt, requires looking at the same observations that seem to confirm natural interpretation and recognizing that they equally or better support artificial interpretation once you allow yourself to consider that framework seriously, requires abandoning comfortable assumption that everything in the sky is natural unless proven otherwise, and accepting that some things might be artificial even when they're trying hard to appear natural. The evidence won't force that transition for everyone. Won't compel acceptance of artificial origin through sheer weight of measurements that are individually ambiguous even though collectively suggestive. Will leave room for those who prefer natural explanations to construct scenarios, however complex or unlikely, that avoid accepting extraordinary conclusion that we're observing technology. Because the standard of proof for extraordinary claims is deliberately high, is designed to prevent acceptance of wild speculation, is protection against being fooled by our tendency to see patterns and infer agency even in random phenomena. But the standard can be too high, can prevent acceptance of true hypotheses when evidence accumulates in ways that are suggestive but not definitive, can create situation where no amount of indirect evidence is sufficient because the bar for direct proof is set unattainably high, where you're demanding artifacts that spell out this is artificial in ways that leave no room for interpretation when sophisticated technology might deliberately avoid being that obvious, where you're requiring level of certainty that might be impossible to achieve through remote observation of object that's designed to evade certain detection. The mass paradox is the strongest single piece of evidence that natural framework is inadequate, is observation that's difficult to reconcile with any conventional process, that forces either acceptance that we made enormous error in some measurements, despite their apparent quality, or acceptance that the object changed fundamentally in ways that violate our understanding of how matter behaves, or acceptance that we're misunderstanding what we're observing because we're assuming natural when we should be considering artificial. And among those three alternatives, among accepting measurement error, or accepting physics violation, or accepting artificial origin, which is actually most extraordinary, which requires smallest stretch beyond what we know to be possible. Measurement error would be extraordinary given the precision achieved and the number of independent observations that all agreed. Physics violation would be extraordinary because conservation of mass is fundamental principle that's never been observed to fail. Artificial origin would be extraordinary because we've never confirmed extraterrestrial technology before. But artificial civilization building interstellar probes isn't physically impossible, doesn't require new physics, doesn't violate any known principles, just requires technological development beyond what humans have achieved. Just requires that we're not alone and that others reached capabilities we're still working toward. That's extraordinary from historical and philosophical perspective because it changes our cosmic context. But it's not extraordinary from physical perspective. It's allowed by everything we understand about how the universe works. So maybe artificial origin is actually least extraordinary option. Is explanation that fits observations without requiring measurement errors we can't identify, or physics violations we've never seen? Is hypothesis that accounts for all the anomalies through single framework while natural explanations require separate special circumstances for each feature? Is interpretation that unifies the data instead of fragmenting it? That realization, that recognition that artificial might be less extraordinary than the alternatives we're trying to maintain, is what could tip the discussion, could shift the consensus from treating artificial origin as fringe speculation that must be rejected unless proven absolutely to treating it as serious hypothesis that deserves evaluation alongside natural alternatives. Could change how we approach observations and analysis and what kinds of explanations we consider viable. But that shift hasn't happened yet, hasn't occurred at institutional level even though individual researchers are increasingly willing to discuss artificial possibilities seriously. The official communications still emphasize natural framework, still treat the mass paradox as puzzling feature that will eventually be explained through better understanding of cometary processes rather than as evidence that we're not observing comet at all. Still maintain that extraordinary claims require extraordinary evidence, even when the evidence is accumulating and when alternative explanations are becoming increasingly strained. The window for additional observations is closing. 3i Atlas is receding. Is moving outward on trajectory that will eventually take it beyond reach of our most powerful telescopes. We have months perhaps, maybe a year or two, before it becomes too faint and too distant to study effectively. Before the opportunity to collect data that might resolve the questions passes, and we're left with whatever observations we managed to make before the window closed. That limited window creates urgency, creates pressure to prioritize observations that have highest potential for discriminating between hypotheses, creates need for coordination and planning that ensures we're making best possible use of remaining time, creates opportunity cost, where every observation that doesn't contribute to resolving the central questions is potentially wasted chance to collect data that might actually matter. But the observations being conducted seem to be following momentum rather than strategy, seem to be collecting data opportunistically rather than executing systematic hypothesis testing campaign, seem to be characterized by individual researchers pursuing separate questions rather than by coordinated effort to resolve the mass paradox and the artificial versus natural debate. That's partly how science works. It's a distributed process where many researchers follow independent interests. But it's also missed opportunity, is failure to organize around the questions that matter most and that have realistic chance of being answered if we're strategic about what we measure and when. The spectroscopic characterization of the outflow is critical priority that could provide definitive evidence about whether we're seeing natural sublimation or engineered propulsion. Detailed spectroscopy, measuring composition precisely, determining what molecules are present and in what proportions, looking for species that would indicate chemical or nuclear processes rather than simple sublimation, looking for isotopic ratios that might reveal whether material has been processed or refined, looking for anything that distinguishes natural outgassing from artificial exhaust. That observation is technically feasible. James Webb can do it. Other capable spectrographs exist. The question is whether telescope time will be allocated, whether the proposal for dedicated spectroscopic campaign will be prioritized over other scientific programs competing for limited resources, whether the community recognizes that resolving the nature of 3i Atlas is important enough to justify dedicating precious observation time to systematic characterization. The trajectory monitoring is another critical priority. Needs to be continuous or near continuous rather than episodic. Needs to track how acceleration evolves with precision that can detect patterns indicating active control versus passive response to environment. Needs to coordinate across multiple facilities to maintain coverage as Earth rotation moves object in and out of view from any single location. Needs to be sustained for months to build data set that reveals temporal structure rather than just snapshots. That requires commitment, requires allocating resources over extended period, requires convincing multiple observatories that this target deserves sustained attention rather than just opportunistic observations when telescope happens to be available, requires overcoming institutional inertia that favors distributing observation time across many proposals rather than concentrating it on single high-priority target. Whether that commitment materializes, whether the investigation becomes systematic rather than remaining fragmented, depends on leadership that might not emerge if institutions remain reluctant to acknowledge that resolving natural versus artificial question is actually important priority, because admitting it's important requires admitting that artificial is plausible, requires accepting that the question is legitimate rather than being fringe speculation that doesn't deserve serious resources, requires shift in how the community thinks about what we're observing and what questions we should be asking. The historical context matters for understanding why the scientific community is struggling with this question, because we've never been here before, never had observational data detailed enough and anomalous enough that artificial origin for interstellar visitor becomes genuinely plausible hypothesis rather than just wild speculation. Oumuamua came close, generated debate about whether its acceleration might indicate light sail or other artificial propulsion. But the data remained ambiguous enough that natural explanations, however exotic, could be maintained without requiring too many special circumstances. The question remained open, but didn't force resolution. 3i Atlas is different, is pushing harder against the boundaries of what natural framework can accommodate, is accumulating anomalies at rate that makes natural explanations increasingly baroque, while artificial explanation remains straightforward, is creating a situation where the mass paradox in particular is so stark, so dramatic, so difficult to reconcile through any conventional process, that continued insistence on natural origin starts looking like ideological commitment rather than evidence-based reasoning. But accepting artificial origin means accepting profound implications, means acknowledging that we're being visited, that intelligence exists beyond Earth, that technological civilization has developed elsewhere and has capabilities we don't possess, that we're not alone and never have been, that the galaxy contains others who think and build and explore, that our cosmic isolation is illusion, and that we're actually participants in larger context we're only beginning to recognize. Those implications are what create resistance, are what make accepting artificial origin psychologically difficult even when evidence supports it, because accepting it requires reorganizing how we think about ourselves and our significance and our future. It requires confronting questions about why visitors are here and what they're doing, and whether they're aware of us and how we should respond. Requires grappling with possibilities that are simultaneously exciting and terrifying, and that challenge comfortable assumptions about humanity's special status. The resistance manifests as methodological conservatism, as insistence that extraordinary claims require extraordinary evidence, as demand for definitive proof before accepting artificial origin, as construction of increasingly complex natural explanations that require multiple coincidences but that avoid extraordinary conclusion, as criticism of artificial hypothesis for being speculative even when natural alternatives are equally speculative but in different ways, as asymmetric application of standards where artificial must be proven beyond doubt while natural is accepted as default even when it struggles to fit observations. That asymmetry is exactly what needs to be challenged, because the question shouldn't be whether artificial origin is proven beyond doubt, should be whether it's more probable than natural origin given all available evidence, should be comparative evaluation of competing hypotheses rather than demanding that one hypothesis meet higher standard than the other, should be honest Bayesian reasoning where we update probabilities based on observations rather than defending priors regardless of what data shows, and if you do that reasoning honestly, if you compare how well natural versus artificial hypotheses account for all the observations without special pleading or motivated reasoning, the artificial hypothesis performs well, accounts for the mass paradox straightforwardly, explains the velocity excess naturally, makes the sudden appearance of acceleration comprehensible, provides unified framework for all the anomalies rather than requiring separate explanations for each feature. The natural hypothesis struggles, requires fluffy comet with exotic structure, requires hidden outgassing that perfectly cancelled during summer, requires measurement errors that affected multiple independent facilities, requires processes that enhanced velocity beyond thermal limits, requires each anomaly to have separate explanation, and requires all these explanations to apply simultaneously to single object, requires stacking circumstances in ways that make the explanation complex, and contrived even though it avoids extraordinary conclusion of artificial origin. Which is more probable? Complex natural explanation requiring multiple special circumstances, or straightforward artificial explanation requiring only that we accept we're not alone. The mathematics of probability favours simpler explanations, favours hypotheses that account for observations with fewer assumptions, favours frameworks that unify rather than fragment, all of which suggest artificial hypothesis deserves serious consideration rather than reflexive rejection. But probability calculations don't compel consensus, don't force everyone to accept same conclusion because people weigh evidence differently, assign different priors to competing hypotheses, have different standards for what constitutes sufficient proof, have different tolerances for accepting conclusions that challenge worldviews, so debate continues, arguments proliferate. Each side criticizes the other for bias or for motivated reasoning or for failing to appreciate crucial aspects of evidence. And while the debate continues, while the scientific community argues about how to interpret observations, 3i Atlas continues its journey, continues moving outward, continues executing whatever trajectory it's following, whether that trajectory is determined by natural processes or by mission planning, continues being what it is regardless of what we conclude about it, The object doesn't care about our interpretations, doesn't adjust its behavior based on what explanations we favor, just operates according to whatever physics or programming governs it while we watch and measure and debate. That indifference is humbling. Reminds us that the universe operates according to reality rather than according to our theories about reality, that our explanations are attempts to understand what's actually happening rather than being determinative of what can happen, that nature or technology does what it does regardless of whether our frameworks accommodate it, and that when observations contradict frameworks, it's the frameworks that need to change rather than the observations being dismissed or reinterpreted to fit preferred theories. The mass paradox forces that confrontation, forces recognition that something fundamental is wrong with how we've been thinking about 3I Atlas. Either the summer measurements were wrong in ways we don't understand, or the object changed in ways physics doesn't allow. Or our assumptions about what we're observing are wrong because we're trying to understand artificial object using natural framework. One of these must be true, and determining which one is the challenge we're facing. The answer matters beyond just satisfying curiosity about single object. Matters because it shapes how we interpret future observations, how we think about other interstellar visitors that will inevitably be detected as our survey capabilities improve, whether we approach them assuming natural origin until proven otherwise, or whether we consider artificial possibilities seriously from the beginning. Whether we design observation campaigns to test natural hypotheses exclusively, or whether we include tests that could detect artificial signatures if they're present. If 3I Atlas is artificial, and we conclude it's natural, if we dismiss the evidence because accepting extraordinary conclusion is too uncomfortable, then we set precedent that makes recognizing future artificial visitors difficult. We establish pattern where even strong evidence is insufficient, where no amount of anomalies forces consideration of artificial possibilities because the bar for acceptance is set impossibly high, where we remain blind to what's actually in our solar system because we're too committed to assumptions about everything being natural. But if 3I Atlas is natural, and we conclude it's artificial, if we accept artificial origin based on evidence that ultimately has natural explanation, then we set different precedent. We establish that we're willing to jump to extraordinary conclusions prematurely, that we interpret ambiguous data as supporting wild speculation, that we don't maintain appropriate skepticism about claims that challenge fundamental assumptions, and that precedent could damage credibility of future claims about artificial visitors when evidence genuinely supports them. So the stakes are high both directions. Get it wrong either way, and the consequences extend beyond this single case. Affect how we approach entire class of questions about whether we're alone and whether visitors might be observable in astronomical data. Affect scientific credibility and public trust, and our capacity to navigate contact scenarios if they arise. Affect everything about how humanity responds to cosmic context that might be more populated than we believed. That's why resolution matters. Why we can't just leave the question ambiguous indefinitely. Why we need to examine evidence rigorously and reach conclusions even though conclusions carry risks of being wrong. Because ambiguity is answer 2, is implicit decision that we can't determine what we're observing, and that decision shapes future actions just as much as explicit conclusion in either direction would. The fluffy comet versus hollow shell debate encapsulates the central tension. Both explain the mass discrepancy. Both provide mechanisms for reconciling summer and winter observations. Both are technically possible given current understanding of physics and materials, but they require different frameworks, different assumptions about what processes created the object and what governs its behavior, different implications for how we think about interstellar visitors and our cosmic environment. Fluffy Comet says nature creates more diverse structures than we've observed in solar system comets. Says formation conditions around other stars might produce objects with very low density and high porosity. Says our mass estimate was wrong because we assumed typical density when actual density was orders of magnitude lower. Says everything is natural and explicable through exotic but possible processes even if we haven't seen them before. Says we can remain comfortable in assumption that we're studying geology rather than technology. Hollow Shell says intelligence creates structures optimized for specific purposes. Says artificial object designed for interstellar travel would minimize mass while maintaining size necessary for functionality. Says our mass estimate was wrong because we assumed solid object when actual structure was deliberately hollow. Says behavior we observe is controlled operation rather than passive response to environment. says we need to abandon comfortable assumption and accept that we're studying technology from civilization we've never encountered. The evidence doesn't definitively favour either interpretation, doesn't provide smoking gun that proves one hypothesis correct and the other wrong, instead provides pattern of observations that are consistent with both frameworks, but that require different explanations within each framework. And choosing between frameworks requires making judgment about which set of explanations is more plausible, which requires fewer special circumstances, which better unifies the observations. Which feels more like it's actually right versus more like it's defending preferred interpretation. That judgment is where reasonable people can disagree, can look at same evidence and reach different conclusions based on how they weigh various factors, based on whether they prioritize simplicity of individual explanations or overall coherence of framework, based on whether they accept extraordinary conclusions when evidence suggests them, or whether they require definitive proof before abandoning conventional thinking, based on all the subjective elements that enter into scientific reasoning, even though we pretend it's purely objective process. The pragmatic response is to design observations that could distinguish between hypotheses definitively. That could provide evidence that clearly favours one interpretation over the other, rather than remaining ambiguous. That could resolve the question through data, rather than through argumentation. And some such observations are possible. Spectroscopy measuring composition precisely, trajectory monitoring revealing control patterns, imaging resolving structure, radio detection finding communication signals, each could potentially provide evidence that makes artificial or natural interpretation compelling. But whether those observations will be executed, whether resources will be allocated and coordination achieved and instruments pointed appropriately, depends on collective decisions about priorities, about whether resolving this question is important enough to justify investments required, about whether the community believes answering it is valuable or whether ambiguity is acceptable outcome, about whether leadership emerges that can organize systematic investigation versus whether fragmented opportunistic observations continue without strategic direction. And time is limited. The window is closing. Each day that passes is day we could have been collecting crucial data but weren't, because decisions weren't made or coordination wasn't achieved or priorities favored other science. Each lost opportunity is chance that might not return. Each delay increases probability that 3i Atlas fades beyond observational reach before questions are answered. The urgency is real, the stakes are high, the need for action is immediate, but institutions move slowly, consensus builds gradually. Decisions require proposals and reviews and approvals that take months. By the time systematic observation campaign could be organized and executed, the object might already be too distant, might already be too faint, might already be beyond the point where observations that matter are feasible. The gap between what should be done and what can actually be organized in time available might mean the opportunity is missed entirely. That would be tragedy, would be failure to investigate the most significant astronomical anomaly in modern history, because we couldn't overcome institutional inertia quickly enough, because we couldn't set aside skepticism about artificial possibilities long enough to take the question seriously and allocate resources appropriately, because we prioritized caution over curiosity and missed the chance to answer a question that might not arise again for decades or centuries or ever. The public interest in 3i Atlas creates opportunity for non-traditional approaches, crowdsourcing, citizen science, distributed observation networks, amateur astronomers with capable equipment contributing data, analyzing publicly available archives, building on work that institutions are doing but extending it through community involvement that doesn't require institutional approval or coordination, creating pressure through demonstrated public interest that institutions can't ignore and that forces allocation of resources even when official prioritization processes move slowly. That's happening to some degree. Individuals are tracking the object, are sharing observations, are discussing interpretations online in forums where specialists and enthusiasts interact, are building understanding that's distributed and collaborative rather than centralized in institutional structures, are creating parallel investigation that complements official science and that might reveal insights that institutional research misses because it's constrained by conventional thinking. But amateur observations have limitations, can't achieve spectroscopic precision needed to definitively characterize composition, can't maintain continuous monitoring required to detect subtle trajectory patterns, can't access radio telescopes needed to search for communications, can supplement professional observations but can't replace them, can create pressure for professional resources to be allocated but can't execute all the observations that resolving questions would require. So the professional community remains crucial, remains the entity that has access to instruments and expertise needed to definitively test hypotheses, and the question is whether that community will rise to the challenge, will recognise the significance of what's being observed, will overcome resistance to considering artificial possibilities seriously, will organise systematic investigation before window closes, will provide answers rather than allowing ambiguity to persist because taking questions seriously feels uncomfortable. The mass paradox will be remembered as either the observation that revealed first confirmed artificial interstellar visitor, or as puzzling anomaly that defied explanation, and that eventually faded into obscurity as object became too distant to study. Which legacy it has depends on what happens in coming months, whether systematic investigation materializes, whether observations that could distinguish hypotheses get executed, whether evidence accumulates that forces consensus, whether we seize the opportunity or watch it pass while debating. The 32 trillion tons didn't physically vanish. Matter doesn't work that way. Physics doesn't allow it, which means either the mass was never there and our calculations were wrong, or the measurements creating the paradox are flawed in ways we haven't identified. Those are the only possibilities that respect conservation of mass, and between them, the first seems more likely. Seems more probable that we misunderstood what we were measuring than that multiple independent observation campaigns all made systematic errors that coincidentally aligned. And if the mass was never there, if 3i Atlas was always lightweight object rather than massive mountain, then the summer silence needs different explanation, needs mechanism that prevented lightweight object from accelerating under radiation pressure, despite being light enough that pressure should have affected it. Natural mechanisms for that cancellation exist but require special circumstances. Artificial mechanisms for that cancellation are straightforward, are exactly what you'd design if you wanted to appear massive while actually being light. So the mass paradox points toward artificial origin not definitively but probabilistically, not as proof that compels acceptance, but as evidence that shifts balance. That makes artificial hypothesis more credible than it was before paradox was recognized. That moves the question from fringe speculation to legitimate scientific inquiry, deserving serious consideration and dedicated resources. That changes conversation from whether artificial is possible to whether it's probable. And probability is what science deals with, is what we can estimate from evidence even when certainty remains elusive. The probability that 3i Atlas is artificial has increased dramatically as anomalies accumulate, has gone from negligible prior reflecting assumption that essentially all interstellar objects are natural to substantial posterior reflecting evidence that this particular object behaves anomalously in ways that artificial explanation accommodates better than natural alternatives, hasn't reached certainty, hasn't crossed threshold where artificial becomes proven rather than probable, but has reached level where dismissing the hypothesis is no longer defensible. That's the state we're in, where artificial origin is probable enough that it deserves serious investigation rather than reflexive rejection, where designing observations to test artificial hypothesis is legitimate scientific activity rather than waste of resources on fringe speculation, where accepting that we might be observing technology from beyond isn't extraordinary leap but is reasonable conclusion from accumulated evidence, where the conversation should shift from whether artificial is possible to what observations would distinguish artificial from exotic natural, and how we execute those observations before opportunity is lost. The visitors might be common, might be standard phenomenon that occurs throughout galaxy wherever technological civilizations develop capability to build interstellar probes, might be infrastructure that's been operating for millions or billions of years while we've been too primitive to recognize it. Might be network we're only now beginning to detect because our instruments have finally reached sensitivity required to notice objects we previously would have missed or dismissed as uninteresting natural bodies. If that's true, if visitors are common and we've just been blind to them, then 3i Atlas is representative, is typical example of what's actually out there, but that we haven't been recognizing because we've been interpreting everything through natural framework, and learning to recognize artificial visitors, developing capabilities and protocols for identifying and studying them becomes urgent priority, because if one is passing through now, others will follow. And being prepared to investigate properly rather than missing opportunities through lack of recognition or inadequate observation strategies is crucial for building understanding of who else is out there and what they're doing. But if visitors are rare, if 3i Atlas is exceptional rather than representative, then missing this opportunity would be particularly tragic. Might be decades or longer before another visitor with properties anomalous enough to force consideration of artificial origin appears. Might be once-in-lifetime chance to actually investigate potential extraterrestrial technology rather than just speculating about whether it exists. Might be opportunity that if lost won't return in our lifetimes or perhaps ever. Either way, whether visitors are common or rare, the opportunity is now, is immediate. Is narrowing as object recedes and observation window closes, and seizing it requires action. Requires decisions. Requires allocating resources and organizing campaigns and executing observations that could answer questions before answers become impossible to obtain. Requires overcoming institutional resistance and methodological conservatism and psychological barriers that make accepting extraordinary conclusions difficult even when evidence supports them. The 32 trillion tons are warning, a signal that something is fundamentally wrong with how we're understanding what we're observing. A crack in the comfortable natural framework that reveals reality underneath might be very different from what we assumed. Our invitation to look more carefully, think more broadly, consider possibilities we've been dismissing. Our challenge to scientific community to demonstrate that we can follow evidence even when it leads to conclusions that challenge worldviews. How we respond to that challenge will determine whether we learn the truth about 3i Atlas, or whether we remain uncertain because we couldn't overcome our own resistance to accepting what observations suggest. Will determine whether future historians describe this period as when humanity first recognized artificial visitors, or as when we had the chance and failed to take it seriously. Will determine our legacy and our preparedness for cosmic context that might be more complex than our isolation-assuming frameworks can accommodate. The mass didn't vanish, but our certainty about what we're observing should have. Should be replaced by humility about how much we don't understand and openness to possibilities we haven't seriously considered. Should motivate investigation rather than defensive rationalization. Should drive us to answer questions rather than protecting comfortable assumptions. Should transform how we think about what's in the sky and what we might be sharing our solar system with. That transformation is beginning. Is happening in conversations among researchers who see the evidence and recognize it doesn't fit. Is happening in public discussions where people ask hard questions about why artificial possibilities are being dismissed. Is happening as pattern of anomalies becomes too obvious to ignore. Is happening whether institutions are ready or not, whether official statements acknowledge it or not. Whether traditional frameworks accommodate it or not. The visitors are here, or were here, or something is here that we don't understand and that might be visitors, or might be natural processes so exotic we haven't conceived of them yet. Either way, our understanding is incomplete, our frameworks are inadequate, our certainty about what we know is misplaced, and admitting that, accepting that we're confused rather than confident, is first step toward actually learning what's true rather than defending what we want to believe. 32 trillion tons. The number is too large to ignore, too significant to dismiss, too paradoxical to explain away easily. It's calling to us, demanding attention, insisting we look more carefully at what we're seeing. Forcing confrontation with the possibility that we're not observing what we think we're observing. And if we have courage to actually listen, to actually follow where evidence leads rather than where comfort suggests, we might discover we're not alone, might discover the galaxy has been populated all along, might discover we're late arrivals to context that's been operating without us for longer than we've existed. And that discovery, that recognition of cosmic context we've been missing, would change everything, would redefine humanity's future, would open possibilities and raise questions and create challenges we can barely imagine, would be the most significant realization in our history, would dwarf every other discovery because it addresses the fundamental question of whether intelligence is unique to Earth or whether we're participants in larger story. The mass paradox might be the key that unlocks that realization, might be the evidence that forces acceptance of what we've been avoiding, might be the observation that future generations point to as when everything changed, when we finally recognized we weren't alone, when the visitors became undeniable, when humanity's cosmic isolation ended and our true future began. Or it might be forgotten, might become footnote about unusual object that defied explanation and then faded away. might be missed opportunity that historians regret, might be moment when we could have learned the truth but chose comfort over curiosity, chose defending assumptions over following evidence, chose to remain blind rather than seeing what was actually there. The choice is ours. The evidence is available. The questions are clear. The window is open. What we do with this opportunity will echo through all our future, will determine whether we're civilization that can accept extraordinary truths or civilization that retreats into comfortable delusions, will demonstrate what we value and how seriously we take the search for understanding about our cosmic context. 32 trillion tons await our answer. Not about where they went, but about whether we're brave enough to accept what their disappearance actually means. The universe is watching to see if we're ready, if we're mature enough, if we're honest enough, if we're curious enough. The test is now. The evidence is clear. The answer is within reach. All we have to do is look. The density calculation is what makes the mass paradox viscerally comprehensible in ways that abstract numbers don't capture. Because when you take the revised mass estimate of 260 billion kilograms and divide by the volume of a sphere with 1 kilometer diameter, you get density that's roughly 200 kilograms per cubic meter. Compare that to water at 1,000 kilograms per cubic meter. Compare to ice at roughly 900 kilograms per cubic meter. Compare to typical cometary material that's a mixture of ice and rock and organic compounds at densities ranging from 400 to 800 kilograms per cubic meter, depending on porosity and composition. 200 kilograms per cubic meter is 1/5 the density of water, is less than 1/4 the density of typical comet, is density that requires the object to be not just porous but extraordinarily porous, requires that roughly 75 to 80% of the volume is empty space rather than solid material, requires structure that's more void than substance, requires building mental picture of object that's less like solid iceberg and more like three-dimensional spiderweb where thin filaments of ice create framework holding enormous empty volume together. And that picture creates immediate questions. How does structure that's 80% void form naturally? What processes during accretion or during evolution create such extreme porosity? Why doesn't gravity compress the structure? Why don't impacts compact it? Why doesn't thermal cycling that occurs during passages near stars cause sintering where ice grains fuse together and eliminate void spaces? All processes that should tend to increase density rather than maintaining the extreme low density that observations require. Natural formation of highly porous objects is possible. We see it on small scales in aerogel, see it in some carbonaceous chondrite meteorites that have significant porosity, see it in frost formations where delicate crystal structures maintain large voids. But scaling to kilometer-sized objects while maintaining such low densities is challenging, requires either that accretion occurred in ways that preserved porosity despite gravitational compression, or that post-formation processes created porosity by removing material without collapsing the remaining structure. The accretion scenario requires very gentle accumulation, requires particles sticking together with minimal compaction, requires that gravitational forces never became strong enough to squeeze void spaces closed, requires that thermal processing never occurred that would sinter grains together, requires that the object formed in an environment where these requirements could be met, which is possible, but requires specific conditions that aren't universal, that might occur in some regions of protoplanetary disks or molecular clouds, but not in others, that make extremely porous objects special rather than typical. The excavation scenario requires material removal after initial formation, requires processes that hollowed out the interior while leaving exterior relatively intact. Sublimation could do this if volatiles deep in the interior sublimated and the gas escaped through porous matrix, leaving void spaces behind. But that requires heating to penetrate deep enough to sublimate interior material without causing exterior to collapse. Requires that the object spent time close enough to star that heating occurred, but not so close that everything sublimated. Requires history that includes thermal processing that most interstellar wanderers wouldn't experience. Either scenario is possible but requires invoking circumstances beyond what typical accretion and evolution would produce. Requires explaining why 3I Atlas formed or evolved differently from other objects. Requires that interstellar environment where it originated was special in ways that created extreme porosity that's rare in solar system bodies. Possible but requiring explanation rather than being obvious outcome of normal processes, The artificial hollow shell scenario bypasses all these challenges, doesn't require explaining how extreme porosity formed naturally, just requires accepting that designed structure was built with internal void deliberately incorporated, because that's optimal for mission objectives. Because minimizing mass while maintaining size is exactly what you'd do if designing object for interstellar travel where propellant mass is precious, and where large cross-section might serve purposes like radiation shielding, or surface area for instrumentation or interaction with interstellar medium. Spacecraft designers optimize mass ruthlessly. Every kilogram costs propellant to accelerate and decelerate. Every kilogram reduces performance or requires larger propulsion system or limits mission capabilities. So designs minimize mass wherever possible. Use strong lightweight materials. Use hollow structures where solid isn't required. Use configuration that achieves necessary functionality with minimum material. Create vehicles that look substantial, but that are actually mostly empty, because empty is how you achieve performance that missions require. Scale those principles to interstellar distances, and the optimization becomes even more extreme, because the propellant requirements for accelerating to velocities needed to cross light years in reasonable times are enormous even for lightweight payloads. Adding unnecessary mass makes missions prohibitively expensive, or impossibly slow, or completely infeasible. So you strip everything to minimum, build shells rather than solid structures, use materials with higher strength-to-weight ratios available, accept that finished vehicle will have density far below any natural object because low density is what makes the mission possible, and if you need the vehicle to have substantial cross-section, if size matters for operational reasons even though you want to minimize mass, then you end up with exactly the configuration that 3i Atlas appears to have. Large volume, low mass, density that requires extreme porosity if interpreted as natural, but that makes perfect sense if interpreted as designed. Structure that looks like mountain from distance, but that moves like feather when forces are applied, because it's almost all empty space surrounded by thin shell that provides form without adding mass. The 200 kilograms per cubic meter density isn't anomalous for artificial structure, is exactly what you'd expect from optimized design where mass constraints dominate configuration decisions, is natural consequence of engineering for interstellar mission, where every kilogram matters and where hollow is optimal, is signature that supports artificial hypothesis while requiring exotic explanation if maintaining natural framework. The thermal properties create additional constraints that distinguish natural porous structure from artificial hollow shell, because porosity affects how heat conducts through object. High porosity means lower thermal conductivity, means heat from solar radiation doesn't penetrate deeply, means interior remains cold even when surface is heated, means thermal lag between illumination and outgassing response becomes shorter, because only thin surface layer heats significantly. Natural highly porous comet should show rapid thermal response, should begin outgassing almost immediately when surface receives solar heating, should show activity that tracks solar illumination closely because thermal conductivity is too low for significant delay, should show brightness variations and gas production variations that correlate strongly with which parts of surface face the sun at any given moment, should show exactly the kind of behavior that rotation-driven heating produces when thermal inertia is minimal. But artificial hollow shell might show different thermal behavior, might have active thermal management, might have interior surfaces that are controlled to maintain specific temperatures regardless of external heating, might have thermal coatings or insulation, or radiators that decouple interior environment from solar radiation, might show activity that doesn't correlate simply with illumination, because system is controlling thermal state rather than just responding to it passively. Distinguishing between these scenarios requires detailed thermal modeling combined with high cadence observations of how brightness and activity vary with rotation and with solar distance, requires measurements that can detect whether thermal response is rapid or delayed, whether it's uniform or shows patterns indicating active control, whether correlations between illumination and activity are tight or loose. All technically feasible but requiring dedicated observation campaigns that systematically test predictions from competing hypotheses, and those campaigns aren't happening, aren't being organised, aren't being funded. Because the questions they'd address are only urgent if artificial origin is taken seriously. If you assume natural origin, if you're confident that some exotic but natural process explains everything, then testing whether thermal behaviour indicates active control doesn't seem necessary. Seems like speculative investigation that doesn't warrant scarce resources when more conventional questions remain unanswered. But if artificial origin is plausible, if the evidence has accumulated to point where that hypothesis deserves serious evaluation, then the thermal testing becomes critical. Becomes exactly the kind of observation that could provide discriminating evidence, that could shift probabilities substantially in one direction or the other, that could answer questions rather than leaving them ambiguous. And the failure to execute these observations, the failure to take artificial hypothesis seriously enough to test predictions it makes, is missed opportunity that might not arise again. The structural stability question provides another angle for evaluation, because extremely porous natural structure faces challenges that engineered hollow shell doesn't encounter. Natural structure relies on strength of ice or rock-holding framework together, relies on grain-to-grain contacts that can break under stress, relies on material properties that limit how much void can exist before structure becomes too weak to maintain integrity. Ice has finite strength, can support only limited tensile stress before fracturing, can hold only limited compressive stress before yielding, can maintain only limited void fraction before becoming mechanically unstable. Calculate those limits using known material properties, and you find that natural ice structure probably can't maintain 80% void, probably collapses under its own weight or under external forces before reaching such extreme porosity. Probably requires that the low apparent density reflects not extreme porosity of solid ice, but rather composition that includes substantial fraction of very low density material like gas or plasma or electromagnetic fields that contribute volume without contributing mass. But those alternatives create their own problems. Sustained gas envelope requires confining mechanism. Can't just have free gas around object because it disperses. Need either very high mass to create gravitational binding, or need electromagnetic fields to create magnetic confinement, or need some process that continuously replenishes gas as it escapes. Natural objects don't typically have mechanisms for any of these, don't generate magnetic fields strong enough for plasma confinement, don't have mass sufficient to gravitationally bind substantial atmospheres. Don't have processes that would continuously produce gas in amounts needed to maintain envelope. Engineered hollow shell doesn't face these constraints. Can use materials with higher strength-to-weight ratios than ice. Can use structural elements optimized for carrying loads with minimal mass. Can use geometries that provide stability despite large voids. Can use active systems that maintain structural integrity through mechanisms that natural objects don't possess. Can achieve configurations that natural processes struggle to create, but that engineering makes straightforward. So the structural question becomes, is 200 kg per cubic meter achievable through natural processes given material property constraints, and given that stability must be maintained through objects' history, or does it require engineered structure using materials and designs beyond what natural formation produces? The answer isn't definitive because we don't know all details of how porous structures behave at large scales and under conditions relevant to interstellar objects. But the engineering interpretation removes concerns that limit natural interpretation, provides straightforward path to configuration that observations require. The comparison to solar system comets provides empirical baseline showing what range of densities natural cometary processes actually achieve. We've measured densities for numerous comets through various techniques. Gravitational perturbations of spacecraft during flybys, mass estimates from outgassing combined with size measurements from imaging, nuclear density determinations from detailed modeling of rotational dynamics, and the results show range of roughly 400 to 800 kilograms per cubic meter for most comets, with occasional examples reaching as low as 300, but nothing approaching 200, nothing showing the extreme low density that 3I Atlas apparently has. The lowest measured densities are still 50% higher than what observations of 3I Atlas require, which means either 3I Atlas is extreme outlier, is object with density lower than any solar system comet, despite comets spanning wide range of formation conditions and evolutionary histories, or it's not actually comet at all and the low apparent density reflects artificial rather than natural origin. Outliers exist, aren't impossible. Sometimes you encounter examples that lie beyond the range established by previous observations, because the full diversity of possible configurations is broader than limited sample captures. So finding interstellar comet with density below solar system range doesn't definitively prove artificial origin. could just mean interstellar formation conditions produce more porous structures than solar system formation conditions did. But outliers become harder to invoke when the deviation is substantial, when you're not just slightly beyond previous range but factors away from it, when you're requiring that formation or evolution achieve something dramatically different from what extensive sampling of solar system bodies ever produced. At some point, outlier explanation becomes less probable than alternative interpretation, where the object isn't a member of the distribution at all, where it's different kind of thing entirely, rather than being extreme example of known category. And 200 kilograms per cubic meter versus 300 minimum from solar system comets is substantial deviation. Is 50% lower density than anything we've measured. Is difference that requires explanation rather than being dismissible as natural variation. Either interstellar environment creates much more porous structures than solar system environment, or the assumption that we're measuring natural comet is wrong, and density reflects engineered structure designed for purposes that natural objects don't have. The trajectory optimization question returns to the controlled versus passive behavior distinction that runs through all these analyses, because if 3I Atlas is extremely porous natural comet, its trajectory should be dominated by gravitational forces with relatively small perturbations from outgassing, that's responding to solar heating according to predictable patterns. The path should show some non-gravitational acceleration, but that acceleration should correlate with solar distance, and with rotation, and with viewing geometry in ways that passive sublimation produces. But if 3I Atlas is artificial hollow shell with active propulsion, trajectory can be optimized, can be adjusted to achieve specific objectives, can show maneuvers that align with mission requirements rather than just responding to environmental conditions, can demonstrate intelligence in how forces are applied to create desired path through solar system, and detecting that optimization, recognizing patterns in trajectory evolution that indicate planning rather than randomness, provides evidence for artificial origin that's independent of mass paradox or density calculations or any single anomaly. The challenge is that optimization isn't always obvious, isn't always dramatically different from what natural processes might coincidentally produce. Requires detailed analysis comparing observed trajectory to full range of possible trajectories that natural or artificial origins would generate. Requires statistical evaluation determining whether observed path is typical of natural scenarios or whether it falls in region more consistent with designed mission profile. Requires computational modeling that's sophisticated and that accounts for all relevant forces and that can distinguish signatures of control from signatures of passive response. That analysis is possible, is exactly the kind of work that orbital dynamics specialists can do, but it requires sustained attention to 3I Atlas trajectory, requires tracking positions precisely over extended period, requires building dataset that captures evolution well enough that patterns become detectable, requires treating questions seriously enough to invest effort needed for rigorous evaluation rather than just assuming trajectory is natural and not investigating whether alternative interpretation better fits observations. And again, that investment hasn't happened at scale needed for definitive conclusions, hasn't been organized, hasn't been funded, hasn't been prioritized because questions about trajectory optimization only matter if artificial origin is plausible enough to justify dedicating resources to testing it. So we're in self-reinforcing cycle where artificial hypothesis isn't taken seriously enough to warrant investigations that would test it, and absence of those investigations is cited as reason to continue not taking hypothesis seriously. Breaking that cycle requires someone with credibility and resources deciding that the evidence has accumulated to point where systematic testing is justified, requires institutional leadership willing to allocate telescope time and computational effort, and researcher attention to question that remains controversial. Requires accepting that investigating potential artificial visitor is legitimate scientific priority rather than fringe pursuit that wastes resources better spent on conventional questions. And that leadership hasn't emerged, hasn't materialized from NASA or ESA or major research institutions that could organize coordinated campaign. Individual researchers are publishing analyses of specific anomalies, are contributing pieces to puzzle, but systematic hypothesis testing program that would bring all the pieces together and that would execute observations specifically designed to distinguish artificial from natural remains absent. Remains something that should happen, but that isn't happening because organizational barriers and cultural resistance prevent it. The public engagement creates alternative path forward, creates pressure that institutions can't ignore indefinitely, creates demand for answers that motivates allocation of resources even when internal prioritization processes move slowly, creates distributed investigation where many individuals contribute observations and analysis that collectively advance understanding, even though no single authority coordinates everything, creates democratization of the question where conclusions emerge from community consensus rather than from institutional pronouncements. That's valuable, is exactly how citizen science can complement professional research, is mechanism that ensures questions that matter to many people get investigated even when institutions are reluctant, is example of how technology enables participation that wasn't possible in previous eras, when astronomical observations required access to equipment and expertise available only at professional facilities. But it also has limitations. Can't replace professional observations that require major facilities, can't achieve the precision and coverage needed for definitive tests of some hypotheses, can supplement and extend and pressure, but can't fully substitute for systematic professional investigation. So while public engagement creates momentum, ultimate answers still depend on professional community committing resources to questions that public interest has highlighted as important. The philosophical implications of confirming artificial origin extend beyond just knowing we're not alone, extend to questions about how common intelligence is, about how technological civilizations develop and spread, about whether interstellar exploration is rare achievement or common outcome of reaching certain capability threshold, about whether the galaxy has been explored thoroughly or whether we're seeing early stages of expansion that will eventually make encounters more frequent, about where humanity fits in the timeline of galactic civilization development, if 3i Atlas is artificial and if similar visitors are passing through regularly, if detection is just a matter of achieving sufficient observational capability to recognize them, then the galaxy might be substantially populated, might have many civilizations at various developmental stages, might have infrastructure for exploration and communication that we're only beginning to detect, might be an environment where intelligence is common rather than rare, and where expansion across interstellar distances has created network we're late to discovering. That scenario has profound implications for humanity's future, for whether we're pioneers or latecomers, for whether our expansion will encounter empty space or will require navigating relationships with others who are already present, for whether we develop independently or learn from examples that more advanced civilizations provide through their technology and through artifacts they've left in our observation range, for whether our trajectory follows path that's unique or path that's been travelled before by others who face similar challenges. Alternatively, if 3i Atlas is artificial but represents rare event, if encounters with visitors are infrequent enough that we might see only one per human lifetime or per generation, then intelligence might be rare, might be achievement that few species reach and that fewer still maintain long enough to develop interstellar capability, might be outcome that requires specific circumstances that don't often align, might make humanity's existence and development more significant as potentially rare example, rather than as common occurrence. That scenario has different but equally profound implications for whether we're alone in practical sense even though intelligence exists elsewhere, for whether expansion will be solitary journey through empty galaxy rather than navigation through populated neighborhood, for whether we're responsible for seeding intelligence across regions that don't currently contain it, rather than encountering existing civilizations that have already spread, for whether our decisions about our future matter enormously because there's no one else who will step in, or whether they matter less because others exist who will persist regardless of our choices. Determining which scenario is accurate, understanding how common intelligence and interstellar exploration actually are, depends on detecting and characterizing more visitors, depends on establishing statistics rather than just encountering single example, depends on building sample that reveals patterns, and that requires developing systematic programs for detecting interstellar visitors as they approach rather than just studying them after they've been noticed coincidentally. Requires building infrastructure for continuous monitoring that catches objects early and tracks them comprehensively throughout their passage through solar system. Projects like the Vera Rubin Observatory, with its legacy survey of space and time, will dramatically improve detection rates. We'll image entire visible sky repeatedly. We'll find objects that current surveys miss because coverage is incomplete, or cadence is insufficient. We'll create catalogues of interstellar visitors that will enable statistical analysis impossible with current handful of confirmed detections. We'll transform our understanding of how common these visitors are and what fraction of them show characteristics that might indicate artificial origin. But detection is just first step. Characterization is where we determine whether detected objects are natural or artificial, and that requires follow-up observations with a variety of instruments measuring different properties. Requires spectroscopy and photometry and astrometry and radio monitoring and all the observational techniques that could reveal signatures distinguishing natural from artificial. Requires coordination across facilities and across time zones and across wavelength ranges to build comprehensive datasets that support rigorous evaluation. The infrastructure for that characterization exists in pieces. We have telescopes capable of making necessary observations, have expertise to design programs and analyze results, have computational tools to model behavior and test hypotheses. What we lack is coordination, is institutional commitment to treating interstellar visitor characterization as systematic priority rather than as opportunistic investigation that happens when individual researchers pursue separate questions, is framework that organizes efforts toward common goals rather than fragmenting across many independent programs. Building that framework requires recognizing that we're entering new era where interstellar visitors will be detected regularly rather than occasionally, where questions about their nature and origin and frequency become answerable through accumulating statistics rather than remaining speculative, where humanity's understanding of cosmic context advances dramatically as we learn whether we're in populated galaxy or empty one, and whether technology is common achievement or rare outcome. 3i Atlas is potentially the example that catalyzes that recognition, that forces acknowledgement that we need systematic approach rather than ad hoc investigation, that demonstrates through its paradoxes and anomalies that distinguishing natural from artificial requires dedicated effort rather than casual classification based on assumptions. That shows we can't just assume everything is natural, and that serious evaluation of alternatives requires investment in observations specifically designed to test competing hypotheses. If that catalysis occurs, if 3i Atlas forces institutional changes that create framework for systematic visitor characterization, then its significance extends beyond just being potential first confirmed artificial visitor. It extends to being trigger that transformed how humanity approaches question of whether we're alone. That created infrastructure ensuring we'll recognize artificial visitors when they appear rather than dismissing them as natural anomalies. That established protocols and methods and expectations that serve us well as encounters become more frequent. But if catalysis doesn't occur, if institutional response remains fragmented and skeptical and resistant to seriously considering artificial possibilities, then 3i Atlas becomes missed opportunity, becomes example that should have taught us lessons, but that we failed to learn from because barriers to accepting extraordinary conclusions proved insurmountable, becomes warning about what happens when evidence accumulates, but institutions can't adapt quickly enough to investigate appropriately before windows close. The choice between these outcomes is being made now, is being determined by decisions about how to respond to mass paradox and accumulated anomalies, by whether systematic characterization programs are organized or whether investigation remains fragmented, by whether artificial hypothesis is taken seriously enough to warrant dedicated testing, or whether natural framework is maintained regardless of how strained explanations become, by whether we seize opportunity or watch it pass. The 32 trillion tons serve as persistent reminder that our understanding is incomplete, that observations don't fit comfortable frameworks, that something fundamental about how we're interpreting 3i Atlas is wrong. They're not going to be explained away through refined measurements or improved analysis if the problem is conceptual rather than technical. If we're trying to understand artificial object using natural framework, no amount of careful observation will make contradictions disappear. They'll persist until we change framework to match reality, rather than continuing to force reality into framework that doesn't fit. That realization is difficult, requires admitting that extensive work done under natural assumption might need to be reconsidered, requires accepting that conclusions drawn confidently might be wrong, not because analysis was sloppy, but because foundational assumptions were invalid, requires humility about limits of our understanding and willingness to revise when evidence demands it, requires exactly the kind of intellectual flexibility that science claims to value, but that in practice is difficult to maintain when revisions are dramatic. But that flexibility is what distinguishes science from ideology, is what makes scientific method effective at converging toward truth rather than just defending preferred beliefs, is what allows correction of errors and incorporation of new understanding, is what ensures progress rather than stagnation. And 3i Atlas is testing whether contemporary science can maintain that flexibility when confronted with evidence challenging fundamental assumptions about cosmic isolation and naturalness of everything we observe. The test is ongoing, outcome remains uncertain, but the evidence is clear. 32 trillion tons didn't vanish. Our understanding of what we were measuring did. And recognizing that distinction, accepting that we might have been wrong about something fundamental, is first step toward actually understanding what 3i Atlas is and what its presence in our solar system means for humanity's cosmic future.